Hello. In this video, I'm going to describe and apply to several examples some methods for evaluating limits using some algebra and some careful analysis. Thus far, I know that we've been using graphs of functions and just using, for instance, Desmos to graph a function and look at it to see what the one-sided and two-sided limits are doing. But moving forward, we might have some more complicated or exotic functions, or we might want to understand really why the graphs look like they do and why the limits seem to be approaching what they do. So we're going to develop some techniques here for more carefully analyzing limits. So I'm going to start with one function, and we're going to evaluate two different limits at two different inputs for that function, just to contrast the two different examples. And I'm going to use this rational function defined up here. Remember, a rational function is a ratio fraction of polynomials. So I see I have a quadratic function at the top and a quadratic function at the bottom. And just for comparison's sake, for your visual learning, I've included the graph over here. But everything that we're going to do in this example and the next one, I'd like it to be so that we don't really rely on the graph to find the answer. I'm just going to point to it to confirm what we're doing, because I know you're in the process of learning how to do this. But moving forward, we don't even necessarily need this graph to do what we're doing in these examples. So let's say I was asked to evaluate this limit as x approaches -2 of this function. Well, seeing that this is a rational function, and based on some of the examples and facts described in the online notes and other examples we've been working on together, I would know that a good first strategy for this, because it's a rational function, is to just substitute, it's to just plug in. Let's figure out what f of -2 actually does, and then we'll see whether that makes sense. You can see there I've started to plug in -2 as the input into the function. In the numerator, I get -2 squared, or 4, minus 3 times -2, so minus -6, or I'm going to write that as plus 6, and then minus 10. Meanwhile, in the bottom, I get 2 times -2 squared, so order of operations, I'm going to square the -2 first to get 4, then I'm going to double that to get 8. Minus 9 times -2, so minus -18, or plus 18, and then minus 5. And now you can see where this result down here is coming from, the 0 over 21. That is, the top of the fraction there is 4 plus 6 minus 10, that's 0. The bottom is 8 plus 8 is 26, minus 5 is 21. And remember that 0 divided by something non-zero is 0. If I have no slices of pizza and I cut that into 21 equal pieces, I still have no slices of pizza. So this is telling me that the point -2, 0 is on the graph, and I can actually see from the Desmos graph, there it is. But it's because when I plug in x equals -2, I do get a valid output, and it happened to be 0, and therefore this limit is 0. And it's been kind of hinted at in the notes, and perhaps in other examples we've done, but the fact that I'm really applying here is that if I have a function that's a nice function, like a polynomial or a rational function, and the output of the function is actually well defined, it exists, it's a real number, and it's some number, let's call it L for limit, then the corresponding limit as x approaches that input A, that limit will actually be that output L. So this is saying that essentially polynomials and rational functions are sufficiently nice. They're pretty nice functions. And in the future, we're going to have a more concrete formal definition for what quote-unquote nice really means. And really, I'll just state it now, and then we'll get into it in more detail later on in the course. But really, the main fact we're going to learn is that if I have a nice continuous function, and it just so happens that polynomials are always continuous, and rational functions are always continuous as long as I don't have a division by 0 problem. So in other words, wherever they are defined, they are continuous. So that's really the fact that's lurking behind the scenes with all of this. Okay, let's see a slightly more interesting example with this same function of a different limit. Let's take the same rational function that I have here, and here's the same graph. I've just kind of shifted over a little bit to show you a different part of the graph. I want to evaluate what happens as x approaches 5. Let's take the limit as x goes to 5 of that function, And you might say, well, let's just use the graph. Why don't I look over here at where x is 5, somewhere around there, and say, isn't there a point right there on the graph? Whatever the height, the y-coordinate of that point is, shouldn't that be my answer to this limit? Shouldn't that be whatever this result is? And the problem here is that if you plug in x equals 5, you get 0 over 0. I will save us the trouble of writing out the details, but if you plug in x equals 5 in the top, you get 0, and if you plug in 5 in the bottom, you get 0 as well. So I have something that's undefined. And so in fact, it looks like from Desmos that there's a point on the graph there, but there's really a hole. It's not fine enough to show me that there's actually a gap in the graph there. There's no point where x equals 5. And yet, it does look to us like if I approach from the left or from the right, there is a very specific y-coordinate of that point, where that hole is where the point would be. And so really what we're going to do in this problem is figure out what that y-coordinate is. Where is that hole? How high is it on the curve? What is its y-coordinate? And so it turns out what we're going to do is factor. You might want to do some algebra practice with these skills, but I'm hoping that you'll be able to relatively easily factor a nice simple quadratic like this, especially because it's 1 x squared in the beginning, so I know I'm going to set up x plus or minus something times x plus or minus something else, and I'm just looking for those somethings to multiply out to -10 and to add up to -3. And perhaps just for a little bit of quick review, there are some details written out to convince you that my factorization does work there. The first terms multiplied together gives me the x squared. The inner and the outer terms multiply together to give me -5x and plus 2x, and those together give me the -3x I wanted to see in the middle. And then the two numbers at the end, the lasts, the -5 times the +2, that gives me a -10. And so that all checks out. And so that might give you a little bit of insight into the process of how I played around with numbers to find that. I'm looking for two things that multiply to -10, that's the purple combination, and I'm looking for the two combinations in the middle, the blue and the green, to add up to -3. Now you could do something very similar with the next factorization I need to do. The only difference is because I have a 2x squared, one of my factors is going to be a 2x and the other one's going to be a 1x. And so there's the factorization that I came up with, and there's some details written out to convince you that it does add up to what I want to see. And now I can take those two factorizations and simplify the whole original rational function, the fraction. And so really what you see there is that I've factored the top and the bottom, and very conveniently they share a factor of x minus 5 in the top and the bottom, so I get to cancel those out and simplify the function a little bit. And so there I've done that cancellation, and you can see that I've simplified the function quite a bit. But I want to point out that when I write equals and equals there, there's a really subtle point, which is my function equals that fraction over there, except at the input x equals 5. My function f of x, as it was defined way back here, doesn't exist. It's undefined when x is 5. And yet this new fraction that we just found does exist when x is 5. And in fact, the output that we get there at x equals 5 is 7 over 11. And that is precisely the height of that y-coordinate of that point. That is the height 7 out of 11. And so that's the result of this limit. And so that's kind of the funny thing about this rational function. It's really this function here. It's really the same as that function, except for one little thing. If you were to graph that function that I've just circled in Desmos, you would see the exact same curve that I have shown on the right half of the screen here. You wouldn't notice any differences. The only difference, and it's very subtle, so subtle that Desmos won't even show you the hole, the only difference is that hole at x equals 5. My function f of x has a hole there, but this fraction, this rational function here that we simplified to, doesn't have a hole. It is defined at x equals 5. So for that reason, this limit does exist and it equals 7 out of 11, even though the function itself doesn't output exactly 7 out of 11 there. Okay, here's a similar but slightly different example that we're going to explore. Here's a limit of something, it looks like another fraction, some kind of rational function, and we're going to evaluate it as h approaches 0. So we're going to try the same thing. We're going to plug in h equals 0, see what happens. As it turns out, that's going to give us 0 over 0. We're going to clean up the fraction, simplify a little bit, and then at the end we'll get to plug in the number h equals 0, just like we did in the last example. And then on the slide after this, I'll go back and show you what it is that this fraction really represents. This isn't just a random math problem to try to trick you. There's a real meaning behind this, and it's going to be super important for us as we move forward in the course and talk about derivatives. There you can see I've plugged in h equals 0. In the numerator, I get 4 minus 2 minus 2, so I get 0. In the bottom, I obviously get 0. So this is another undefined situation when I try to plug in the limiting input value. And so I have to do something else. I have to do something different if I want to evaluate this limit. And so what we're going to do is expand and simplify and combine some like terms in the numerator, and then hopefully do some factoring and canceling, much like we saw in the last example. I suggest pausing the video for a second, trying that on your own, and then unpausing to see what I've done, and we can compare. There, I've done that simplifying in the numerator. I expanded the 2 plus h all squared. That's where all of these terms in the parentheses are coming from. Make sure you can do something like that quickly and easily on your own. A couple of number terms combine. I have 4 minus 2 minus 2, so all those zeros go away. And then I have a 4h minus h, so there's where the 3h comes from. And then I have that lone h squared that has no other like terms to cancel with. And so I can actually do one more step and factor out an h from both of those things. That's going to be helpful in the next step. There, I've simplified the numerator to be h times 3 plus h, and the denominator was just exactly h, so those factors of h cancel out, they disappear, and I'm left with just 3 plus h, and now it's pretty easy to just plug in h equals 0 into that expression and say in the limit I'll get 3, and that is the result. So what we're finding is that plugging in h equals 0 from the beginning gave me something undefined, something that didn't make sense, something that was 0 divided by 0. And yet doing a little bit of algebra, simplifying the fraction a bit, brought me to a situation down here where I was able to just plug in h equals 0 and get a result. Now you might be wondering, why would something like this happen? Why would I get a situation where it seems to be undefined, 0 over 0, but then it actually is something, a specific number, like 3? Well, like I said at the beginning, this limit up here actually represents something. This is not just a crazy dark magic math problem that we've created to mess with your head. It comes from somewhere. And so let me talk a little bit about what that is. It comes from this particular quadratic function. Let's say I looked at the function x squared minus x. And so its graph is this parabola curve that you see over here on the right. And let's say I have chosen the point where x equals 2. I'm going to call that point P. That's the base point. So you can see the coordinates there, 2, 2. If you plug in f of 2, just like I've written out there, that's why you'll see that the y-coordinate of that point is 2. And then let's say I take some other point, I'm going to call it Q, and I'm thinking of it as nearby 2. So I'm going to express its x-coordinate as 2 plus some quantity h. Now on the graph over here I've shown you the specific point at x equals 3, so I'm thinking of that as the input 3, the x-coordinate of that point the point Q, is 2 plus 1. In other words, that point is one horizontal unit away. It's to the right one step along the x-axis. And that's what that quantity h represents. And so on the graph you can see its y-coordinate is 6. That comes from plugging in x equals 3 into the function way back here. But I've just shown you that one picture to have something to look at. I really want to explore what happens as I change that value of h. So I've shown you in the picture the specific number, the specific value h equals 1, but I'd really like to write down the slope of the line between those 2 points, thinking of h as a variable. So I'm thinking of that quantity h as a variable, so I'm going to write up there next to the point Q, 2 plus h, comma, f of 2 plus h. And I want to find this slope of the line between those points P and Q. I'm going to call it m, because we usually use that for slope. and I'm going to write p and q in the subscript just to remind myself that it's the slope of the line through those points. And remember that the slope of the line is just the ratio rise over run. So what's the rise between these 2 points? It's the vertical separation. It's the distance between their y-coordinates. It's what I get if I plug one of them into the function, and I subtract what I get plugging the other one into the function. And so there's the numerator of that expression, the 2 plus h all squared minus quantity 2 plus h. That comes from f of 2 plus h. And the 2 comes from the fact that I already know f of 2 is 2. That's the y-coordinate of the point P. And there I've just highlighted those quantities to show you where they're coming from. But also notice how in the denominator I have 2 plus h minus 2. That's the run. That's the horizontal distance, the separation along the x-axis between the 2 points I'm talking about. So one of them has x-coordinate 2. One of them has x-coordinate something nearby, 2 plus a little bit, 2 plus h. And so their difference, their subtraction, is just h. And what do you know? Look at that. That's exactly the expression from the previous slide. And so what we realize now is that that fraction that we saw in the limit on the previous slide turns out that has a visual meaning, and it's the slope of this secant line that passes through the point P that I'm thinking of as fixed, and this other point Q that I'm thinking of as variable. So I could wonder what would happen if I take that other point Q and I were to make it get closer and closer to the point P along the graph as I drag it closer. How could I make that happen? Well, that's taking a limit as h, the separation left and right horizontally between the points, gets closer and closer to 0. Or in other words, if I make the x-coordinate of q get closer and closer to 2, I would have to make h get closer and closer to 0. And as I do that, the output of this fraction is going to give me the slope of a secant line, and then as I get really, really close to 2, it's going to eventually show me something that's really close to the slope of the tangent line. And so in fact, what we just discovered on the previous slide is that the slope of this tangent line right there is exactly 3. If I were to perfectly sketch that tangent line right there, that line has slope 3, based on what we discovered in the previous limit that we evaluated on the previous slide. And so that's the meaning behind this example that we were doing earlier. This kind of limit where I have h approaching 0, and it's producing a 0 over 0 undefined thing, so I have to do some other algebra or analysis to figure it out. That's going to happen a lot as we go forward in this course and try to find tangent lines like this, when we try to find derivatives a little bit later. And that's going to happen a lot because if I asked you what's the slope at this point, well, you can't take the coordinates 2, 2 and the coordinates 2, 2 again and plug it into rise over run and have it make sense. You would get 0 over 0 if I use the same point twice. There's no rise and there's no run. So now it's not shocking that I got a 0 over 0. I actually had to do something different to evaluate this. Okay, here's another slightly different type of algebra method or technique you can use in some cases. This one is another example where I'm going to get a 0 over 0 if I plug in x equals 0. I'll spare you the details here. You get 0 over 3 minus root 9, so 3 minus 3. So it's undefined. But there's no factoring to be done here. Good luck factoring x any further into something that you can cancel out with the bottom, like we saw in some earlier examples. Instead, I'm going to look to do something that algebraically changes the nature of this expression that will eventually allow me to plug in x equals 0 and have it do something. So you can kind of see where this is going in preview with all the stuff I've outlined on the slide, but let me show you and write out some details here in the middle. The trick here, the technique I'm really going to apply is something called rationalizing the denominator. I'm going to multiply by something so that the bottom of the fraction doesn't have any roots in it anymore. And so I'm using the idea of this difference of squares factorization that you've probably seen and used many times to go this way. If I saw a difference of squares, I know I can factor it like that. But today we're going to do it backwards. I'm going to essentially I already have an a minus b. I have 3 minus root x plus 9 in the bottom. I'm going to multiply by the other one so that it turns into a difference of squares. And that will be helpful because in my case, the b is that square root. So b squared is going to have no root in it. And that's going to be super helpful. There, I've started to write out the multiplication. You can see the canceling happening in the middle. I have a negative 3 times that root plus 3 times that root. Here's the difference of squares thing happening. And then in the final step there of simplifying, I have that root x plus 9, all of that root squared. So I have just the quantity underneath, x plus 9. So I have 9 minus all that, the 9 minus 9, they cancel out. And I have a minus x. So that's really just the result after all that. And so let me write out really what I'm doing in this with the whole fraction that I started with in the limit. And so everything that I've written above that purple line there was just that multiplication. Underneath the purple line, I'm showing you what I'm really doing to that fraction that I started with inside the limit way back in the beginning. I'm not really changing it, I'm multiplying it by 1, but just in a really crafty way to make things cancel out and simplify so that I can do what I want to do, which is plug in x equals 0. The way this fraction is written right now, plugging in x equals 0 leads me to something undefined. But by multiplying by 1, essentially this fraction of a quantity divided by itself, I know that I'm not really changing the value of the fraction. For any possible x value that I could plug in and have it make sense, I'm multiplying by 1, so I'm not really changing what the value is. But the reason I've chosen that particular fraction is that it simplifies the bottom to just minus x. And I can see there is that factor of x in the top, and that's that canceling happening right there. And so I'm really left with a negative 1 because of that negative down there, times that 3 plus root x plus 9 in the top that I multiplied by. And now I can finally plug in x equals 0 into this whole expression that I had back there. So I get negative 1 times 3 plus root 0 plus 9, so root 9 or 3, and I get negative quantity 3 plus 3, I get negative 6. That's the result of this limit. That really is correct. So this is a slightly different algebra technique, but it accomplishes at the end the same goal as what we saw in earlier examples. Plugging in a number, an input x gave me a 0 over 0, an undefined thing. Doing some algebra cleaning up led me to a situation where I could plug in the x value I wanted and get a number output. Okay, here's a totally different type of technique that I might need to use to evaluate some limits. This doesn't involve factoring or rationalizing a denominator or anything like we were just seeing in those examples, but it will show up in some examples. So the first graph up at the top here is similar to something that we've seen before. It's in the online notes, it's in one of my videos, and it's been on some of your homework problems. A limit like this does not exist. This cosine of 1 over x squared function essentially takes something like the cosine wave, and it kind of scrunches it all up like an accordion, and it makes that whole oscillation going all the way out to the right, it makes it happen like super fast coming into x equals 0. It's squishing up that cosine wave like an accordion and making it all happen around x equals 0. And so what we see is that the limit doesn't exist because I have a whole bunch of points up here that output positive 1, and meanwhile a whole bunch of points down here that output negative 1. And so my limit can't approach both 1 and negative 1 at the same time. And even meanwhile, I also have a whole bunch of outputs that are 0. So I can't have a limit that approaches 3 different things all at once. And so that's why this limit does not exist. It fails to approach a specific value because it's approaching, essentially, in a very real sense, it's approaching everything between negative 1 and positive 1 all at once around x equals 0. Now notice the difference between that function here and the one down at the bottom. The only difference is that multiplication by x in the front. That is the one change from the function on the top to the function on the bottom. But look at how different the graph is. I can still see that infinite wiggling, like the cosine oscillation that I was seeing in the graph above, but it looks like it's not oscillating between negative 1 and 1. It's kind of, it looks like it's like shrinking and getting closer to 0 in height around x equals 0. And as it turns out, that is exactly what we're going to show. I'm going to go through the details on the next slide. But for now, I just wanted to show you the graph and to say that it depends on 2 different facts. We're going to apply the Squeeze Theorem, a fact that I'll state and use on the next slide, and the fact that cosine is a bounded function. So let me start with that one. Cosine is a bounded function in the sense that its outputs are bounded between 2 numbers, 2 specific numbers. When I plug in whatever the heck you want into the cosine function, I know with 100% certainty that what comes out, the output of the function, is some number between -1 and +1 inclusive. I can never have the cosine of something output 2 or -5 or anything outside of that range of -1 to +1. That's the sense that I mean bounded. Another way to see that and think about it is that the graph of the cosine function is bounded there in between the lower limit of -1 and the upper limit of +1. The cosine function's graph is always bounded between those two horizontal lines. And I wrote cosine of x here, but it really doesn't matter what's inside. Cosine of x squared, cosine of 1 over x squared, cosine of whatever. Cosine of anything is between -1 and +1. That's something you need to know about the cosine function and its relationship to the unit circle and right triangles and things like that. So that's one fact we're going to need in this example. The other thing we're going to need is something called the Squeeze Theorem. It says that if I have three functions like this, where one of them is always squeezed between the other two. So if I have that h function in the middle squeezed between f and g, so it's always greater than or equal to f and less than or equal to g, and here's a visual to picture that. Let's say I have g at the top and f at the bottom and h in the middle. If I know that h is always between the other two, and let's say I know that f approaches a specific limit L, and g approaches a specific limit, the same value L, then what choice does h have except to be squeezed to the same place? So here I'm imagining c, the input x value that I'm approaching as 0 for the example that I've drawn. So let's say that as x approaches 0, f of x approaches 0. I have the point at the origin there. And let's say g also approaches 0, the origin. And if I know that h really is squeezed between those two, where else is it going to go? It can't escape outside above the g function, and it can't escape below the f function. And if it's pinched between them, it's got to be squeezed down to the same limiting value. That's why this is also called the sandwich theorem, the squeezing theorem, the pinching theorem, things like that, because you can kind of have this visual associated with it. Now for our specific example, what we can say is, remember my function was x times cosine of 1 over x squared. I can say that with 100% certainty it's less than or equal to x, because whatever the heck cosine is doing, I know that at the absolute biggest it's going to be +1. So this is like having x times, at the maximum, +1. And I know that on the lower end, whatever the heck is going on inside the cosine function, it can't output something below -1. So like lowest case, minimum scenario, cosine is outputting -1, and I can still say my function is bigger than or equal to -1 times x. So that's why I get to write this chain of two inequalities here and say this is true all the time. For any input x that you could possibly plug in, that function we're thinking about is going to be between -x and +x. But think about what the graph of those two functions look like. Over here, I have y equals -x, and over here I have y equals +x. And notice how the cosine function that we're dealing with, x times cosine 1 over x squared, is squeezed in between those two. No matter what x I'm plugging in, it's always in between them. And since they both approach 0 at x equals 0, my cosine function is squeezed or pinched down to that place too. It has to stay in between those two diagonal lines that intersect at that place, so that function has to be squeezed to the same place. I put a link to the Desmos graph down there at the bottom. I suggest you open that up in another tab and play around with that graph and look at it, zoom in and out, and see what's happening around x equals 0 to convince yourself of this. But try to be on the lookout for using this fact, especially when you have a bounded function. If there's like a sine or a cosine involved, or even a tangent inverse, we know that's another bounded function, try to let this technique at least come to mind, and it might be helpful. Okay, really quick at the end here, I just want to show you that although it's been really helpful to develop all of these techniques we have in this video, a bunch of algebra techniques, factoring, rationalizing the denominator, things like that, and the squeeze theorem we just saw. Although it's really nice to have all of those techniques, they aren't going to be a full set of tools for us to build all of the structures we want to moving forward. So that's why I have the title here, that algebra and the squeeze theorem can't do everything for us. And so here's a very natural question that I can ask you and pose related to what we've been studying, and we'll see that the techniques we have so far are insufficient to determine exactly what's going on, and so we're going to have to do some more stuff in the future. Let's think about this exponential function, f of x equals 2 to the x. That's this exponential growth curve happening in the graph that you see. And let's focus at its y-intercept at the point 0, 1. Let's say I want to find the slope of the tangent line right there. So let's say I were able to draw this perfectly tangential line like that. What is the slope of that tangent line? If I draw that line down there, what is its slope? Well, based on the techniques we've been developing, I would look at some secant lines. Let's pick some other point somewhere else on the graph. I've picked a specific example here where the x-coordinate is 2, and then I've graphed the secant line that goes through that point and the other one we care about, 0, 1, the y-intercept. And then I could find the slope between those by doing rise over run. So for this example, it looks like the rise is 4 down to 1, so it's 3, and the run is 2 over to 0, so it's 2. And 3 over 2 is 3 halves, or 1.5. That's why I mentioned that right there. In this table here, I'm showing you what happens if I make that point at not x equals 2, but like x equals 1. Sorry, on the graph, so at like x equals 1. Or something really close to 0, like 0.1 or 100th or 1,000th. If I make all of those points get really, really close to 0, what's happening to the corresponding slopes of the secant lines? They go down, they're decreasing, but eventually it kind of settles at 0.693 something, and then it seems like it's 0.6931. It looks like it's approaching a specific number, but I can't really tell what it is. What is that something? Well, I'll tell you that it turns out it's exactly the natural log of 2. That's that number that it's approaching. And it turns out that's the slope of that tangent line there. But sorry, there just ain't nothing that we've learned in this video or so far in this class that's going to tell us why it's exactly that number. All we can do so far is what I have outlined in this slide, creating a little table, looking at some numbers, and maybe we'd magically guess that it's natural log of 2 for now, but that's not a great method. So we're going to have to develop some techniques going forward beyond just the ones that we have in this video, although they are very helpful for many of the examples we'll be doing. Just as the previous slide, here's a link to a Desmos calculator at the bottom. I recommend you pull that up and play around with it yourself to see what you can discover. Okay, see you next time.